Hello, my name is Dylan Hacker, and today we will be discussing, deriving, and coding a problem today. This problem is going to factor in the temperature of a uniform bar over a specific amount of time. And to start off, we're going to be using the heat diffusion equation with no heat generation, which goes something like the change in T, the change in temperature over the change in time, is equal to the thermal diffusivity times the second derivative of temperature over the second derivative of x, which is position of the bar at any time. And from this, we're going to be finding a solution and proving that that solution is a valid solution for this derivative. So we have T is going to be equal to E to the negative thermal diffusivity times K squared times T. And this is going to be multiplied by E to the IKX. So we can put that in parentheses if we wanted to. All right. And with this, we're going to be solving why this is a valid solution to the heat diffusion equation that we just wrote out. So on the left side here, we're going to take the derivative of this equation according to time. So if we do that, then that means the first part comes out, so we get negative thermal diffusivity times K squared, and then E to the negative alpha, that goes there again. And then, of course, we're going to keep this on that side as well. And this is going to be equal to the second derivative. So we get the second derivative according to x, right? So if we take the second E right there, and we are going to do it twice, so we get I squared K squared. I forgot, we got to put our thermal heat diffusivity in there as well. So that goes up front, and then I squared K squared E to the IKX, and then we got to keep our E to the negative K squared T. So once we have that, we do get I squared, and I is an imaginary number. So I is equal to the square root of negative 1, and if we square this, we just get negative 1. That's supposed to be 1. And so on this right side, we get negative 1 times the thermal diffusivity times K squared, and then EIKX, E T, and then we get the same thing on the other side, which proves that these two expressions are equal and that this is a valid solution for our heat diffusion equation. Let me finish writing this out for you. And K in this problem is any real number, any integer. It's valid for all integers, and we just proved that with our little derivation right above. So next we'll be moving on, and we'll be finding a finite differencing solution using this as well. Alrighty, and we're back. So now we have our heat diffusion equation, and we're going to be deriving that equation, and we're going to be plugging in some values once we find it into our code, and we'll be plotting that. So first, let me draw you what I am thinking of right now. So we have this bar right here, and this bar is going to be cut up into X amount of a random, any number of slots or positions So in this case, we have position 0, 1, 2, 3, and 4. And at each of these positions, there's going to be a different temperature. And we have on the left side, this is just a rough example, we'll have this is going to be 30 degrees Celsius, and then this is going to be 100 degrees Celsius. This is just an example. We won't be doing this exact problem in our code, but I just want to make you guys more familiar with the problem that I'm going through. So what we have here is a different temperature. So we have the temperature T at a position J, which is going to be 0, 1, 2, 3, 4 in this scenario, one of these numbers down here, at a time n. So the time is going to be as the variable n in this case. So now we want to derive our heat diffusion equation right now. So we have the change in temperature over the change in time is equal to the thermal diffusivity times, I'm going to expand this part right here, so d over dx times dt over dx. Alrighty, so now we are going to put some variables in here using our t at position j time n. So on the left side, what we have is t at, and this is going to be the over the change in time, so we're going to be changing the time variable. So t at n plus 1 at point j minus t at n over at point j over delta t, the change in time, is equal to the thermal diffusivity, and this is the derivative of a derivative, right? So say we want to find the derivative of this point, it's going to be the derivative of that point as well, so it's going to be this one and then minus this point over here. I'll show you what that looks like. It's going to be at the temperature at, and this is over position, so our n is just going to be n, and this is going to be j plus, let's make that lowercase, j plus 1 minus the temperature at time n of j, and this is over the change in location, or the change in x, and then this is going to be, we'll put this in parentheses, minus temperature at time n of j minus the temperature of at time n, of course, j minus 1, and this is also over the change in x. And it's the second derivative, so this is also going to be over the change in x. So that is the equation, and we're going to have to simplify this equation a little bit, and we want to get t j n plus 1 by itself on the left side. So what that's going to look like, first, let's start by simplifying the right hand side of the equation. So we get the thermal diffusivity, and then the top part is going to simplify since they have a common denominator. It is okay. We have T n j plus 1 minus 2 times T n j plus the temperature at time n j minus 1. So all I did was combine that, and the 2 comes from 1, 2 right there, and then the minus a minus obviously becomes a positive number. And this is over delta x squared, because the common denominator comes together and then it divides it again. So you just have delta x squared on the bottom right there. And now we want to move this delta t onto the right side, so we just multiply this by delta t, and then we're almost there. We want to put this temperature at time n at position j on the right hand side as well, so we're going to add that right here. We get temperature time n j t j n plus 1. So now we have the temperature at time n plus 1 at position j is equal to this right here. Alright, now we're going to add a variable to make this equation look a lot simpler, and this is going to be r. And r is equal to, it is thermal diffusivity times delta t over delta x squared. And we will be using this value of r in our code. That is why I'm explaining it now. And we will be coding here in just a moment. Let me go ahead and write down our final equation. So we have the temperature at time n plus 1 of position j is equal to the temperature of the same position at the previous time, which is just n, plus our variable r times the temperature at j plus 1, so the position to the right, at time n, minus 2 times the temperature of j at n, plus the temperature of j minus 1, so the previous spot at time n. And there we have it right there. We will be coding this out in just a moment. And when we code it out, we'll also be plotting. And there is one minor flaw we have with using this system instead of a future system, which I'll implement later on in the video. Alrighty, and we're back. We're now going to be coding the problem that we just walked through before. So the first thing I always like to do is import numerical Python into our code. I like to name it as NP, keep things nice and simple. So now we're going to have to write down some of our variables that we will be using. So let's look back at what we worked on before. So we're going to need some variables for increments. So nx, which is the number of increments that we're going to have, we're going to set this equal to 50 because we have a 50 meter bar and it's going to be cut up into 50 different sections. Next, we're going to need a time element, so we're going to have a variable for the number of time, the number of time increments. So we want this to be equal to 2000, which is a lot, but it'll show a much smoother curve when we get down to that into plotting. So now that we have that, we're going to be needing a number for alpha, which is our thermal diffusivity. So we want A equal to, we'll say 1. We like to keep the numbers nice and neat. And there is one flaw in doing this, and I'll show you that flaw here later on once we get to the plotting. So now we're going to need numbers for dt and dx. So for dt, we're just going to be using 0.5. And for dx, we're going to be using 1. So now that we have those out of the way, we can begin to create our variable for r, which r is alpha times the change in time, so dt, times divided by dx squared. So now that we have those basic variables out of the way, let's think about what we're going to be doing. So we're going to we have a bar, and we're going to be measuring the temperature, diffusivity, the thermal conductivity of the bar as it goes in. So we're going to be needing an array for the temperature that has the same amount of elements as our increments. So we want T, which is how we're going to be tracking the temperature. We want T to be equal to NP, and we want a base value for all of the temperature in the bar, which, so our shape is going to be NX. And the temperature we're going to use as the base is going to be 20 degrees Celsius. And let's make sure that has that on it, so it is able to change as a double or a decimal and not as an integer. So once we have that, we do know two values. We know the value at index of 0, so the very left part of the bar, which this is going to be equal to 50. We know the value of the far right side of the bar, which we're going to be using the index of -1. That just goes back 1 from the beginning, which is the end. So we can put in as many increments up here in our x or nx column as we want, and this value will always be 80. So now let's add a code right here to look at what T is. Let's click Shift Enter to make sure that all runs. And so we have exactly what we want. We have 50 different elements in here the index of 0 being 50 and the index of the last index being 80. So now let's get rid of that. So now we want to go ahead and plot what we're doing, right? So we have to, so from, I believe it's plotly.subplots, we're going to be importing make subplots. Right there, shift enter. And for the variable for our subplot, I always like to use fig, short for figure, right? And it's going to be make subplots, and we are just using one row and one column for the subplot. So now that we have that, we want to set fig, and we want to add our first plot to it. So to do that, we have to do add underscore, I believe it's scatter. And we need an x variable. So our x variable, we want to create an array, right, with this many increments going from 0 to however many nx's. So in order to do that, let's click enter right there, and go right here. So x is going to be np.arange, and we just want it to be an x, right? And we're going to multiply it by dt, or dx, I mean, which is the change in x, right? So we get the exact amount of increments that we need, and it all lines up perfectly. So once we have that, we want x equal to x. We want our y equal to the temperature, and we want to name it. We want to name it, let's just go with initial for now, initial, and let's do fig.show, to see if everything works nicely, and it is working well so far. So we have our index of 0 to 50, our index of 49, which is the 50th element in the code, to be 80. So that is running perfectly so far. And now we want to be able to implement the equation that we found before in our work, right here. So that works out nicely. Let's do for I in range, and we want our range to be our time, right, starting with 1. Because we know the time, or we know this is at time 0. This is the plot for time 0, right? So we want to go nx plus 1, or nt plus 1. And we're going to be plugging in our equation now. So we want at time n plus 1, so this is what we're going to be finding. We want the indexes of 1 to -1. We are excluding the index of 0 and the index of -1. So we put this number right here. It is going everything up to, but not including, right? And then we're going to be doing that as well, which is just whatever it's set to previously. The index of 1 to -1, plus, and we have our r times, and then put this all in parentheses. We want j plus 1. So what does j plus 1 look like? So if we look at our bar rate right here, j plus 1, if we're focusing on 2 right now, j plus 1 is going to be 3. So in order to do that in our code, we want to add 1 to this, so it equals 2, and then we want everything up to the very last index, so we just go leave that blank, which makes sure that it picks up everything after that, or everything starting with the second element all the way to the last. So now we want -2 times our t of 1 to -1, and then we want plus our t, and this is j minus 1. So what does j minus 1 look like? If we're focusing on 2 again, we just jump back 1. So we subtract 1 from our indices. So we do everything up to -2. So now that we have that, we do have 2,000 time increments, right? When we don't want to plot that many. because that will just look like a huge mess on our graph. So we want to make an if statement. So if, and we're going to be using the modulo to get only the amount that we want. And so if this is I modulo 100 means whatever I is, divide that by 100, and we're going to say if the remainder of that is 0, so if it is a factor of 100, or if 100 is a factor of it, then we can go ahead and use it. So now that we have that, we want to copy and paste this up here. Copy and paste. And we don't want to name it initial because we already have initial, right? So we're going to name it just based on what the I value is. And to do that, we just do F right there. And we want a mode as well on here. We're just going to set the mode equal to lines so that they're all lines and they're all going to be different colors. And it's going to look super cool, right? And we name? Oh, I forgot a comma. That'll do it. Whoa, look at that. And now we can see based on at what time value it is, it does get to a straight line. Boom. This is what it is supposed to look like, right? So at time 100, we have all these different values inside the bar. We can see that the heat is going inwards, right? We can see it all diffuse inwards. So now that we have that, I did say that there is one problem with using this method, and that is the value of R. So let's say we go to 0.05. Let's see. And it doesn't work correct. I mean, that is kind of right, but we go to 1. What is this? What is going on here? Why is it like this? Why is it doing this? Let's go closer. Maybe we can find, like, I don't know, 0.55. It's all crazy. Let's go like 0.01. Let's check and see if that's closer. We can see it starting to have some sort of waves, which you would definitely not expect, right? This is not what you're looking for if you're actually performing an experiment like this. This is just unrealistic. So the more we bump it up, right, the more it's going to have these crazy waves. But if we go down, let's go, I don't know, 0.45. Look, it looks perfectly normal. So anything under what looks like this 0.5 point, right, is normal. Even when I went down to 0.05, it looked relatively normal, right? You wouldn't say this is completely wrong, like if we bump it up to, I don't know, 0.51, right? This is just crazy. This is so unrealistic. Look at that, 10 to the 30th. Why is it like that? In just a moment, I will be going over what value of R, because that's what we're changing, right? The value of R. So what value of R is our barrier to where we are able to use this formula right here and be able to get an accurate answer, or what we'd expect. Alrighty, well, I'm gonna see you in just a moment then. Alrighty, and we're back. So now that we know this solution is not a valid solution because our R has a restricted value, we're going to find what value of R it actually is using the von Neumann stability test, right? So we have this expression right here, and we found that R, when we change R and it goes above a certain value, the graph just doesn't work. We get temperatures of unrealistic amounts, right? But what value of R is it that the temperature, or that this equation stops functioning correctly? So as we saw for before, we saw for what the T, one of the solutions for T is, right? So we're going to go ahead and use that and some identities to solve for what R can actually be, right? So we're going to go ahead and write down what T is down here. So I do not want red. So T equals e to the negative alpha k squared times T times e to the I believe it's kx, but let's go ahead and make sure up here Yes, it is. And so this is for t, but what are we doing? We're solving for t n at position j at time n, like we said. So e to the negative delta, and this is getting to be k squared delta t, right? Because this is a change in temperature, times j, so whatever our time is, right? And then e I k delta x squared right here, and then we're going to put n right there. So now we can, using this right here, we can go ahead and simplify by putting in these values up into our equation right above. So for when we're solving for r, our left side, in this case, is not going to matter, but we can go ahead and solve for what it would be anyway. So we get Tn plus 1 of j is equal to e negative alpha. We're using the left side here because the time is actually changing, right? And when our time changes, we're just going to get k squared delta t. So our j is going to be positive in this, or our n, apologies, this should be n right here, and this should be j. I messed up my variables, right? So our j, so j, or n in this case is going to disappear because it's going to be positive, so that means our delta value will be positive, right? So for our left side of the equation, we're just going to keep this the same for now, and j equals, and then Tn at position j is going to be right there. And this is where our r value comes in, and we get e to the I k delta x. And what is happening to our delta x? It's going to be plus 1. That means our j is going to be positive. So we just leave it like that. And then this is plus 2 Tnj, and then plus j minus 1. What is j minus 1? It's going to be negative e to the negative I k delta x. Alrighty, now that we have that right there, we want to find out what e to the I k delta x actually means using an identity, right? So e to the I k delta x is equal to cosine of k delta x plus the I sine of delta x, or k delta x, apologize. And then e to the negative I k delta x is going to be equal to the cosine of negative k delta x minus the I sine of negative k delta x. But since these cancel out right there, when we add them together, we just get 2 cosine k delta x, because those will both, this in parentheses will end up being a positive value. So we get that right there. So we want to go ahead and simplify this just a little bit. So we get t to the n plus 1 j equals t to the n, and we want to take out t n of j, so we get times 1 plus r, and now we're also going to take out r. We want this to be 2r, right? And then we want cosine of k delta x minus 1. So I just simplified it, but plugging that in and simplifying it just a little bit, we get this expression. Once we get this expression, what do we want set equal to what, right? So this value right here, we do not want it greater than 1, right? We want this to be less than 1. So we can go ahead and set this to r cosine k delta x minus 1. I think I got that in there correctly. So once we get that, now we want to move this one over here. Okay, so we get 2r plus cosine k delta x minus 1.
Oh, I did not mean to put plus there. This should be times. Apologize for that. Cosine times. We have our final right there. So once we go ahead and get that, we can go ahead and simplify this, and r is going to be less than 1/2. So for our r value, which if we remember correctly, we get alpha delta t over delta x squared. This value right here, with the thermal diffusivity, we cannot have it be greater than 1/2, as we saw in the code just a little bit ago. If it's greater than 1/2, then the stability of it is inaccurate completely. It is not stable at all. So in just a moment, I will be showing you a method to solve this using the Crank-Nicholson method, as well as we will be coding that out for a more stable solution for any value of r. So now that we got the value of r, we can go ahead and move on to the Crank-Nicholson method, which takes an average of the temperatures at from time n and time n plus 1 at points j plus 1, j, and j minus 1 again. So what that looks like, it's going to be the same equation as we used up here, right? With some added features to the right-hand side of the equation. So let's go ahead and get that down. So we got the temperature of n plus 1 at point j, which is still what we're solving for, n, the temperature at time n at point j, plus, and instead of using r here, I'm going to actually put in what it is, so the thermal diffusivity times delta t over delta x squared. And then this is where a little bit of a change comes in, right? So we get T at N at J plus 1 minus 2 times the temperature at N of J plus the temperature of N, or at time N at J minus 1. So that is the same thing as we solved for up here. And this is where the variation comes in for the Crank-Nicholson method. So we do that, so we're going to be doing the average, right? So it's going to be T n plus 1, J plus 1 right here. And we do the same thing, except for all of these are going to be at time n plus 1. So we have times the temperature at n plus 1 of J, and then we got plus the temperature of n plus 1 at n plus 1 of J minus 1. And the average, we just divide this by 2, and this is where a new value for r comes in, because this 2 is actually going to be moved over there because it is a constant in this case. So we just go r is now equal to the alpha times delta t over 2 times delta x squared. Alrighty, so basically we just added a 2 on the bottom that came from the average right there, right? So now what we're going to do is we're going to be simplifying this a little bit, and to do that we're going to be moving all of these t n plus 1s onto the same side, which is over on the left side here, right? So we get t times t at n plus 1 at j, and then it's minus r of t n plus 1 j plus 1, plus 2 times t n plus 1 of j minus r, I forgot the r right here, so that's 2r, minus r times the temperature n plus 1 of j minus 1. And this is going to be equal to its counterpart at t time at the temperature at point n minus these addition and subtraction signs are going to be flipped, right? Because that's just the equation up there. So now you got t at time n, point j, plus r times t n plus, or n here in this case, right, of j plus 1, minus 2 times r t n of j, and then plus r times the temperature at point n, j minus 1. Alrighty. So now that we have that, we're going to want to simplify this equation using a little bit of identity, right? With the Euler's identity with this value up here, because we're going to be plugging in this value, this solution right here, to get commonalities between both sides, right? And then we can go ahead and go over and do this exact same thing again, to where we get 2 cosine k delta x. But in order to do that, we have to simplify this down. So we get t at n plus 1 at point J is going to be, let's see here, multiplied by, right, because we're taking that commonality out of the equation above. So we get minus r e, and then we're only switching delta x here, right? So that means delta t in our solution is going to be 0, so it's not going to count towards anything in this. So we get negative, or positive, let's see. It's positive, let's see, if it's negative, it's j plus 1, we get positive, correct? Yes. So j plus 1, this is going to be I, and then, whoop, you almost got away from there. And then it's going to be I believe k delta x. And then we're going to do plus, and then this is just 2r, right? And then it's going to be minus r times t, or we're simplifying this, so it's going to be e negative, because it's j minus 1 here, right? I k delta x. And this is all going to be equal to t of n of j times e, or r times e to the I k delta x minus 2r t n j, but that is going to be out, so it's just 2r here, right? And then plus e to the negative I k delta x, right? So now that we have that equation out there, what exactly we're solving for? We're still solving for the same thing, which is the t at the temperature at time n plus 1 at point J. So we're going to be moving this part right here over to the left once we simplify it. And we simplify it the same way that we do up here. So it's going to be, this right side is going to be tnj, and then this is going to be times, we can take an r out of there as well, right? Just like we did up here, right? And then this is going to be 1 minus 2 cosine of k delta x, just like we did up here, remember that? Minus 1, right? And then this is going to be over 1 minus, or 1 plus in this case, 2 cosine k delta x or this is 1 plus, apologize, the r goes inside here, right? 2 times r. And then this is minus 1. So once we have that right there, and this is all going to be equal to tn plus 1 of j, right? And then we have this in big tnj. So now that we have that all right there, we can go ahead and start simplifying this a little bit. So we know that cosine of k delta x, right? This, or we can add the minus 1 on here. This is always going to be positive, right? Because this can be 1 to negative 1, right? 1 to negative 1, right? So no matter what this is, this will always be a positive value. So we're just going to call that portion, we're going to call it, this is going to be set as variable y, and the same on the bottom. So we get 1 minus 2r times y over 1 plus 2r times y. And now that we have r, or now that we have r almost by itself, right? Because that's what we're solving for, is r. We get 2ry, right? So we know that r is also always going to be positive because just the equation itself, it's always going to end up positive. So this will always be greater than 0, right? So now that is, we can call this 2ry. We can set this to a variable of z. So we get 1 minus z over 1 plus z. And can we prove that this is always going to be less than 0? Because we have to have this portion right here has to be less than 0 no matter what, right? Can we prove that that is less than 0, assuming that z is always positive? Because we know that y is always positive, we know r is always going to be positive, and so that means we know that z is always going to be positive. So can we prove that this expression right here is always going to be, less than 1? I apologize. This has to be less than 1, is what I meant to say. Can we prove that this is always less than 1? Yes, we can, because no matter what positive value you put in there, it's minus that is plus, it's always going to be less than 1. Alright, we will be coding this out. I'll draw a couple more pictures to illustrate how we will be able to code this out and get some graphs for it for the Crank-Nicholson method. And then once we code it out, we'll see how the graphs look. All right, now that we solved the Crank-Nicholson equation, we're going to be laying out some of the basic matrices that we will be using in our code. And by doing this, it'll help understand the code and where we go from there much easier. All right, so starting off, we have an index of 0, 1, 2, 3, and 4, and 5, as I wrote out right here. This is just a rough example. This is not exactly what we'll be coding, but it gives the basic idea for our code so that we can take this and put it on a much bigger scale. So what we do, we have this equation I got from right above, right up here, right? From the Crank-Nicholson, right? So what we have is we're going to be creating the two matrices. So one on the left side, we got this right here, and this will be happening at, we'll say, T1, T2, T3, T4. All right, so we have that right there, and what it does basically is it's going to be controlling the R values. So as you can see, for T1, we're not going to have this first value, right? Because that's plus 1. So we'll start off with 1 plus 2r right there, and then right next to it, it will be negative r, and then 0 for the rest of them. And then for the next row down, we'll have, this time it's negative r to start, coming from that first t value right there on the left side of the equation. And then we'll have the 1 plus 2r, and then we'll have the negative r, and then 0 again. And this will just continue all the way down the line, shifting over 1 as it is t n plus 1. So these are all at n plus 1 time values, right? So we can fill in zeros for these, and then negative r, and then 1 plus 2r, and then again negative r, and then this one's negative r, and then this is 1 plus 2r. So exactly like that, right?
And what is this going to be equal to? Well, we have to set it equal to the right-hand equation as pictured right above, right? So this is at time n, though. So we have this. And so for the right-hand equation, at j of, let's see, we got r at t2, because that's the j plus 1, time of n, and then we're going to do plus 1 minus 2r right here, times of the temperature T of 2, or of 1, I apologize. These are all supposed to be, let's see. No, that's j plus 1. So this is supposed to be 2. This is at 1, because that's what we're searching for, because we already have the temperature at time equals 0. So we already have time 0, we'll call it, I don't know, 50, and then time, in this case, we'll do 5, or is going to be 80, right? So we already have the temperature at time 0. And then this is at n, right? Time at n. And then plus is going to be r times the temperature at position 0, which we have, that's 50. Time n, we don't really need that because we already know that the temperature at that point 0 is always going to be 50. And then we just do this all the way down again. So we got r t3 n plus 1 plus 2r, or minus of time 2 plus rt1, and then you get the picture. It goes all the way down until 5, right? Or 4. So, and then we get t4n plus 1 minus 2rt3 plus rt1 t5 plus 1 minus 2rt. And then this, obviously, this is going to be 1, this is going to be 2, and then this is going to be 3, because I messed up. This is supposed to be the temperature at 4. Alright, so we have that right there, which is going to be we're going to call this the B matrix, and then this is going to be the A matrix. But we're missing something, right? Because since we already know the temperature at the 0 point, right, the leftmost part of the bar and the rightmost part of the bar, we can go ahead and move this one over, right, since we already know this. And we know this one for the first part, because at 1, when j equals 1, we'll get 0, right? J equals 0. So we'll come down here and we add plus r t equals 0. So that right there is coming from this point. And then at the very last spot, right, we have to add the temperature at r times the temperature at 5, because we know that right there, right? And that gets shifted over as well. So since those are already known values, we can go ahead and add them to the equations. So now that we have these matrices out of the way and all drawn up, we can go ahead and start over to the code. All right, now we can begin to code out for our Crank-Nicholson method. As you can see, we're using the same line of code, the same file, right? Because we'll be able to compare the two graphs if you'd like. And we're going to be using the same information, the same starting information as before, so we can go ahead and copy and paste that over, right? So with the Crank-Nicholson method, we do have one change to this initial part of code, and that this needs to be divided by 2 again for our R value, because in this scenario, R has a restricted value in which if it goes over 1/2 or 0.5, then this graph becomes super crazy, right? And with our new Crank-Nicholson method, R can be whatever value it wants to be, right? So now we can go ahead and begin coding out the matrices, which we solved for over here in the OneNote. This is A and B, and what A is doing is taking a 2D array where we're storing all these values, all the diagonal values, in 3 separate arrays within the same array, right? So what that means is going to be, we're going to set a equal to numpy, and then we're going to set all these initial values to 0, and then we'll do double parentheses because we do want a 2D array, and we'll do nx minus 2 because we are excluding the 2 external increments, right? The 0 index and the last index. We already know the temperatures for those, so we do not need to solve for those. And with these matrices, as you can see, it's going to be the first index of this 2D array is a list of 48 different elements in another array. And this is what the 2D array looks like. And we're going to be setting each of these to what we found over here with our negative r, our 1 plus 2r, and then our other negative r diagonals. So for our first index, need brackets there. For this index right here, the index of 0, right, we're going to be setting all of these to negative 1, except for the initial value, right? Because if we look at this, there's no r over here, right? That's going to be 0. Or right there, right? There's 0 right there, right? So we want to set everything past 1 to equal to negative r. So let's go ahead and take a look at what a looks like now. As you can see, we have exactly what we need to be, right? The negative 0.25, which is our current r value, is all set to all the values except for this initial one right here. And we're going to be doing this for the next 2 indices of the array, right? So for the index of 1, it's going to be all the values because 1 plus 2r is in all of the values. 1 plus, here we'll do parentheses, 1 plus 2 times r. And then we need to add the last index, which is the index of 2. And it's going to be the opposite of the initial, the one that we did at index of 0. It's going to be everything up until the last one. So not including that last one is going to be negative r. And then let's go ahead and take a look at r. And this is, or a, I mean, and this is our current 2D array value for a. And what we're going to do next is we're going to be creating our array for b. And once we create our array for b, we will be able to do our solve banded, which solve banded is a linear algebra addition to SciPy, which is an element of Python that you can import library-wise. And it will be able to solve our 48 independent equations very easily, very simply. It does not take very long at all. You can solve up to hundreds of thousands of independent equations to choosing. But here we would just be doing our 48 because 50 minus 2 is 48 because we have 48 unknowns, right? We need to find the temperatures of all of the increments in between. So for our B array, we will need to set a list of zeros, and it's nx minus 2. Right, and then for our b value, we're going to be using, so notice how all of these, they go up by 1. So it's just this right part of the equation that we solved up there. So we get r times the temperature, and then it's j plus 1. So that means we want everything from 2 after, plus 1 minus 2r. We got to put this in parentheses. 1 minus 2 times r times the temperature of all of the middle pieces, right? So we want 1 to negative 1 because we already know the index. We already know the temperatures of 0 and the very last index, so we don't include those. Just like we did up here. It's basically the same idea going behind that right there. And then plus the r times the temperature times, or of the index of everything up to -2, right? Just like we did up there. So we can go ahead and shift enter that and take a look at B. Now this is what B is right now, but this is not what we found beforehand, right? Because these two values right there had a little bit of additions too. We had to add these R times 0 because we already know that temperature at index 0 and temperature at 5. In this case 5, which is the last index. And so we get that from that value, right? That value as we explained beforehand. So we got to go ahead and add those in. So we got the index of 0 is going to be equal to the current index of 0 plus R times the temperature of index 0. And we can go ahead and copy and paste this. And it's going to be the same thing right here, except for we're going to do -1. We want the very last index. No matter how long, how many increments, how long our T array is, this will always make sure that we have the last index, right? So now if we shift enter that, shift enter B, you can see our values have changed right there. And now what we can go ahead and do is go ahead and import our solve banded. So solve banded comes from the library of scipy.linalgebra, linalgebra, I believe, and then we're going to import solve banded. Nice. Shift enter that, make sure that goes through. And now we want to go ahead and see what solve banded does first, right? Before we implement it in our code completely, we want to go ahead and see what it does. So we go from L to, okay, so we go from 1 to 1. We want our first matrix to be A and then B. And look at that, it comes out, and these are all of our current temperatures that we have running through the initial effects of that, right? And now what we're going to do is create a for loop, right? For I in range of, we'll go nx plus 1. And then let's go ahead and tab this, and we want T from 1 to -1 equal to that, right? But we also need our B values to update while we do this, because since these are going to change, I in range, we need a thing there. We want our B values to update, so we can go ahead and copy and paste this down here, and now make sure our B values update every single time. And now we need to graph it, right? We want to create our initial graph. So let's do fig2, since we already used fig1 up here, we want a fig2. We can go ahead and copy and paste this, actually, with adding a fig2 behind it. Fig2, fig2. So let's go ahead and run that. And we want fig.show down here, just to fig.show. Oh, we need to add scatter. Add scatter, we did. We added scatter right there. Why is it not pulling up? Let's go ahead and copy that, and then, wait, we can. Oh, our X value, we need a new X value. Right, because this. Let's do fig.show again. And there we go. Now it is showing, except for it is showing all of the values. We don't want these values. Why is it doing that for me? Oh, it's because our x values, right? We want, I didn't change this value. This is what I need to change right here, x2. Still is t values should be updated. Oh, I did fig show. I'm silly. We need fig 2 show. Okay, there we go. So what I did right there was did fig show, and it was showing me this graph again, and I didn't realize that I forgot to add the 2 right there. So I need a fig 2 dot show, and that'll show us our entry graph right here, our initial graph. And now that we solved all this, we want to go ahead and be able to plot this. But we don't want to be plotting it for every single increment, where we have 2,000 and we did nx plus 1, so we have 2,000 increments, right? And for time, and we don't want to plot 2,000 different lines. So we're going to be doing the same idea up here as the if when I is divided by 1,000, which is this modulo, and it equals 0, we want to go ahead and add scatter. Add underscore scatter of x equals x2, y equals t. And then we're going to name it. We're going to do mode is equal to lines. And then we're going to name it well, I forgot the equal sign apparently. Equals. We're going to name it based on what the I value is, right? So let's go ahead and run that. We have to make sure that this is tabbed over so it registers in that. And it's equal, we'll do that. And it is not showing up right away because the fig show is all the way down here. Let's go ahead and put it at the very bottom. Fig2.show. And that is only coming up as 0. NX, because I did NX, we want NT. That is a major mistake. So let's go ahead and run it again, and look at that. So we got all of the values in here, right? And this is a much better model than that because it slowly creeps, right? So this is exactly what we're looking for. Using the Crank-Nicholson method, we figured out how to not have a restricted R value. So thank you guys so much for watching. I hope you guys enjoyed, and I'll see you in the next one.